Okay, so that last time we worked on movement of charges, which we called current right here. I'm going to skip a few chapters just because this is probably a better chapter. Since this will be the last one I'll go over, I'm going to move up to chapter 28. So skip the section. I think we had one on magnetism. We'll skip that one. And we had one on electromagnetic waves. Skip that one. We're going to go right up to reflection and refraction. So hopefully you can see yourself in this chapter right here. So let's look at light hitting. Let's just look at reflection first. Light hitting a mirror right here. When light comes in and bounces off of a mirror, the law of reflection is that the angle that you're coming in at is the same as your angle you're coming out. These two angles are the same right here. It's kind of like throwing a ball against a wall. The angle coming in is the same as the angle coming out right here. This comes from something called least time, the law of least time. When an object goes from here to here, and it has to bounce off the mirror, light always wants to do it in the shortest time. Well, since you're going the same speed the whole way, the shortest time just happens to be the shortest distance. So you notice the light doesn't come over here and go up. That's a longer distance. That would take more time. So light, if he wants to bounce off the mirror, this is the quickest way to do it. And that's the way light does it, which means that these two angles are the same. It's called the law of reflection. I equals R right here. Now, how come I can't see myself on this piece of paper right here? This paper reflects all the light on it. How come I can't see myself? It's not a mirror. Well, it's because this paper is kind of bumpy right here. It's too bumpy right there. And when the light hits it, it's not all it's kind of bouncing around. We call that diffuse reflection. Here, it's so smooth on a mirror that it all goes together right here. And if I can get those bumps down to less than 1/10 of the wavelength of the light, it'll act like a mirror right here. So if you notice, if you go up and look at your satellite dish, if you have a satellite dish, you can't see yourself in the satellite dish because the wavelength of those waves hitting it are pretty big right here. So they don't have to make it real smooth right there. If they were using visible light, you'd be able to see yourself. It'd look like a mirror right here. So now that we have this law of reflection right here, and we'll assume that our bumps are small enough so it acts like a good mirror. What's the shortest mirror required to see your whole body right here? So you don't want to waste mirror space right here. Well, what do? You go down to the mirror store and you look at yourself in the mirror and have someone mark off where they see your feet and your head right here. So here's the person. I'm not going to worry about, I'm just going to say, here's a shoe and there's the eyeball on the top of his head. That's all we need right here. Now to see your eyeball, you look straight ahead right here. So you need a mirror that's at least the height of you. But to see your feet, you don't have to look down at the feet or down here. Since the angle of incidence equals the angle of reflection, this angle coming in is going to bounce up right here. So you see your feet right there. You see yourself you only need a mirror half as big as you to see your entire body. Does that mean that you're only half as big in the mirror? How else are you going to fit in there? Well, you can't be half as big, because I remember seeing I Love Lucy, and Lucy, this is when they had Harpo Marx on, and she pretended she was his mirror image right here. She wasn't half as big. The problem is you don't see yourself on the surface of the mirror. You see yourself the same distance behind the mirror. So you would see yourself way back here. So you'd see your shoe way down there and your eyeball way up there. But you only need a mirror half as big as you to see your entire body. So let's say you go into your bathroom right now and your mirror cuts you off right here. If you walk back, you don't see any more of yourself. Why? Because the distance has nothing to do with how much you see right here. Try it right there. Okay, that's for flat mirrors. But what about curved mirrors? Let's say we have a spherical curved mirror right here. You take it out and you point it at the sun. The nice thing about the sun is it's so far away, all the rays come in parallel right here. When they run in and the angle of incidence equal, that's still true, the angles, they all seem to go through a single point right there. We give that point a special name. We call it the focal point. And we call this distance the focal length, this length right there. Now, for a telescope, this is very important because telescopes, we don't want to make things bigger, we want to make things brighter. And so you notice we took all this light and we concentrated into that little spot right here. So that little spot, if you put your eye there, that's going to be quite bright right there. That's the whole purpose of a telescope. Now, if you went up to Mount Palomar, the giant telescopes, they would put their eye right there. But for regular, you go buy a telescope, it's Scopes R Us or whatever, you can't put your eye there, you block the light. So usually what they do is they put a little mirror here to bring the light out to the end, and then you look through the side. Now, normally when you buy a telescope, you want, if you're going to go down to whatever, Scope City, you want a big focal length right there. This length to be big, because that way you can magnify things better. You're not going to be looking at the edge of the universe, you're probably looking at planets, and the more you can magnify it, the bigger it looks through the eyepiece right there. This is considered a real image. What do they mean by real image? That means the rays actually went through that spot, so we call that a real image. When you were looking at yourself in the mirror, you saw yourself way out there, the light never went through you, so they call that a virtual image. So if the light actually goes through where you see yourself, we call it a virtual image. If it doesn't go through it, it's a virtual. If it does, it's a real image right here. Who was the first person to come up with a telescope like this? Newton. It still survives today. He did everything right here. So this is reflection. Again, it's just incidence equals angle of reflection. Now we can talk about refraction. Refraction is when light goes into a material. And a good analogy is when light goes into a material, its speed changes. And again, remember, light wants to go between 2 points in the shortest time. So suppose, I'm going to look at this analogy. Suppose you're at the beach. This is the beach, looking down from up above. So this is the sand, this is the ocean. Here's a lifeguard over there. And you got a person out here that can't swim very well, right there. And let's say he looks like he's drowning, so what does a lifeguard do? He wants to get to that person in the shortest time, not in the shortest distance. Well, since he can run faster on the sand, and he doesn't swim as fast as he can run, he'd rather go down a little bit further and then cut in right here. He doesn't want to go all the way down and cut in. This would be the quickest way he could get there. This would be the shortest distance if you went in a straight line. If these two speeds were the same, then you'd go in a straight line. But since you go slower here, you kind of move over that way a little bit right here. And so these two angles are not the same right here. The angle of incidence, the faster side, wherever you can run faster, has got the bigger angle, and wherever you go slower has got the smaller angle. Well, this is exactly what light does when it wants to go from one material to another. If we're talking about, let's say you're looking at now the water level's this way, and there's a fish under the water. And this light from the fish wants to get to your eyeball. Well, light goes slower in water and faster in air. So to get to your eyeball in the shortest time, it will actually go up and over. That's a little quicker than going in a straight line. Well, your eye doesn't know the light bent, so you think the fish is right there. That's where he appears to be, but he's really there. So things appear shallower than they actually are. So if you're out spearfishing, don't aim right at him. You better aim below him. I don't know how many people, cavemen must have died because they kept aiming right at the fish. You have to aim below the fish to hit him right there. Maybe it was the cross-eyed people that saved us right here. If we look at a mirage, when you go out into the desert right here. Now, I'm not talking about a lemonade stand. I'm talking about a real mirage right here. Usually, remember we said when ground gets really hot, it's got a low specific heat, the air gets hot, the air's hot here, and it's not so hot up here, it's just warm. Light goes faster in hotter air, why it's less dense. So light says, I can get to your eye a little bit faster. Instead of going in a straight line, if I make this little dip and then come back up. So not only, so I don't see this tree, if there's some tree out there or some mountain, I don't see it up there, I see it over here. So I kind of see the reflection. And that's exactly what a puddle of water would do. You almost think there's a puddle of water halfway between you and some distant object. And as you get closer, you never get any closer to that because you're always this is always halfway in between. You'd never get there. Okay, so Mirage, or this is just refraction. You just stick a pole in the swimming pool and you'll notice that it dips. It would actually dip upward right here, right? Because things appear shallower. Now, if we look at the three colors of light, red has the longest, green, medium, blue, violet would be the shortest, but I didn't have a violet pen right here. But these are the wavelengths right here. And remember, if you have a shorter wavelength, you can see smaller things. So when you send all of these colors through some material, this guy's going to see smaller things in the material, so he's going to go slower right here. So the shorter the wavelength, the slower you go. The longer the wavelength, the faster you go. So if these three colors came into a block of glass, the red would come out first, then the green, then the blue, right here. And since that would mean that when you go into material, if they all go at different speeds, they're all going to take different paths, right here. So since the shorter wavelengths moves slower in transparent materials, the blue will refract more than the red. So if we're looking at like a prism, send in white light. White light is made up of all the colors put together. The blue will bend the most and the red will bend the least. That's why you get the whole rainbow right there. We call this spreading out of light, we call it dispersion right here. We can look at it for a lens. For a lens, just right here, this is a convex lens right here. This is what you'd have if you can't see up close right here. You're farsighted right here. Now normally when you send in light parallel, like from the sun, it all goes through a point over here. We call that the focal the focal point. That's the focal length. But different colors bend different amounts, and so the blue will give you a focal point there and the red will be a focal point there, so it kind of give you a blurry image. So lenses, which is what your eye is too, you cannot make a perfect lens right here. We call this chromatic aberration. You can't grind the perfect lens, but even with the perfectly grinded lens, you're still going to get messed up stuff. That's why big telescopes use mirrors and not lenses, because of that problem. You don't have that problem over here. Okay, now if your lens is the opposite, that is, it's fatter on the top and skinnier in the middle, kind of goes like like this. We would call that a concave lens, and that's for people who can't see far away right here. We would call that nearsighted person right here. So okay, so there's the lens right there. Now we can kind of, if we see, well, where do we see these rainbows? Well, in a rainbow right here. In a rainbow, what do we got? We got water droplets. There's got to be some water droplets in the air. We got to have the sun up too, right here. Now when the light hits the droplet, it's going to reflect and refract, but different colors are going to bend different amounts. And so the blue might bend here and the red might bend there. And so if you looked at it, you'd say, oh, that's a blue droplet. If you dip down a little bit, you say that's a red droplet. This one up here, the red goes into my eyes and the blue is above my head. So I would say that's a red droplet. If I jumped, I'd make it blue right here. But you notice you see blue here, you see red there. And it's not just this way, it's all the way across. So you get a whole arc. And if the earth wasn't in the way, you'd have the whole circle right there. So there is a rainbow right there. Now I should come back and say, you know, if this angle increases, that one increases. You notice this one's going to hit 90 degrees before this one does, right here. When this guy hits 90 degrees, that means the light just goes straight across, and anything bigger, it's going to act like a mirror. So if you're underneath the water, let's say you're a fish underneath the water, and you look too far over this way, you're going to see the bottom of the pond right here. There'll be a ring around where you can see out, but if you look too large of an angle, you're just going to see the bottom. Okay, so they call that the critical angle right here. Okay, so this is the last stuff we'll have on the course right here. Okay.